3 billion miles from where you are sitting right now, a small frozen world is doing something no telescope has ever caught it doing before. It is not moving where models said it should move. It is not glowing the way physics said it should glow. And somewhere in the data streaming back from the James Webb Space Telescope, a research team found a signature in Pluto's light that does not belong to any molecule ever cataloged by human science. Not water, not methane, not nitrogen ice. Something else, something with no name. For decades, Pluto sat at the edge of what we could actually see. Even the Hubble Space Telescope, the sharpest eye humanity had built before Webb, could only resolve it as a blurred model disk, a handful of pixels hinting at light and dark patches nobody could properly explain. Astronomers spent years arguing over what those patches even were, competing models, proposing frost caps, tectonic scarring, or compositional streaks, none of them testable with the instruments available at the time. Then in 2015, NASA's New Horizons spacecraft finally flew past it, and for a few frantic hours, Pluto stopped being a smudge and became a place. Mountains of water ice rising kilometers into a nitrogen sky. A heart-shaped plain of frozen nitrogen so smooth, it suggested geological activity far more recent than anyone had predicted. A hazy blue atmosphere layered dozens of miles above the surface, visible in New Horizons' parting shot as the spacecraft looked back toward the sun, backlit and unmistakable, on a world so small and so cold it should not have been able to hold on to an atmosphere at all. That flyby was supposed to close the book on Pluto. Instead, it opened questions nobody had thought to ask, and the mission team spent years afterward simply working through the backlog of data, discovering new features and images taken years earlier, because a single flyby, however spectacular, could only capture a fraction of what there was to find. Now, a decade later, James Webb has turned its infrared eyes toward that same distant point of light, and it is not confirming what New Horizons found. It is complicating it. Because unlike New Horizons, which saw Pluto up close for a matter of hours before racing on toward the Kuiper belt, Webb sees Pluto the way it truly exists across time, wavelengths. New Horizons cameras were never built to capture chemistry hidden in bands of light invisible to human eyes, and largely invisible even to the spacecraft that once flew directly past it. New Horizons showed us Pluto's face. Webb is starting to show us what is happening beneath it. Here is where the story actually begins. Earlier this year, a team of planetary scientists led by researcher B. Bezard pointed Webb's two most powerful spectroscopic instruments, NIRSPEC and MIRI, at Pluto and at Saturn's giant moon Titan. Spectroscopy is not photography. It does not produce a picture, it produces a fingerprint of light, a graph of exactly which wavelengths a surface absorbs and which it reflects. Every known chemical compound in the universe leaves its own unique signature in that graph, and for over a century, matching those signatures has been how astronomers identify what distant worlds are actually made of. What the team found, buried in the spectrum of both Pluto and Titan, was an absorption line centered at almost exactly 11 micrometers, a dip in the light. A place where something out there was swallowing a very specific wavelength of infrared radiation that nothing else in the solar system swallows in quite that way. The team ran it against every cataloged spectrum of known gases, known ices, known organic compounds. Nothing matched. Not close enough to explain what they were seeing. The absorption was broader and shallower than a typical molecular signature, structurally unlike anything in the reference libraries built up over decades of laboratory spectroscopy. In their own words, submitted through the preprint server archive, the researchers stated plainly that they could not find any previously published band that corresponded to what they were looking at. Two completely different worlds, one small and airless with barely a whisper of atmosphere, the other wrapped in a haze so thick it hides its own surface, and both of them are showing the same unexplained fingerprint in their light. That is not something you expect from coincidence. On Pluto, the signal is roughly 3 times stronger than it is on Titan, suggesting whatever is producing it exists there in much greater abundance. On Titan, the signal is not even spread evenly. It shifts in strength depending on where the telescope is looking, denser in some regions, fainter in others, as if this unknown substance is not just present, but distributed, patterned, shaped by something happening on the surface itself. Scientists have a name for compounds like this before they're identified. They call them tholins, complex organic residues formed when sunlight and cosmic radiation break apart simple molecules like methane and nitrogen and stitch the fragments back together into something new, something the outer solar system seems to manufacture in staggering variety. Titan's orange haze is built from tholins. Pluto's reddish terrain likely owes its color to them too. But a tholin with this exact spectral signature, at this exact wavelength, has never been synthesized in any laboratory on Earth, and never been seen on any other object Webb has studied. Whatever it is, it may be entirely new to science, not new to the universe. New to us. Think about what that actually requires. Every laboratory on this planet capable of producing and analyzing tholins Every archive of planetary spectra collected across more than 4 decades of missions to the outer solar system. Every published reference band from Voyager, from Cassini, from Galileo, from ground-based observatories with their own infrared instruments, checked and cross-checked, and none of it lines up. That is not a small negative result. That is a wall of accumulated human knowledge about outer solar system chemistry, and this one signal walks straight through it without matching a single entry. Researchers do not casually publish a statement admitting they cannot identify something. It is, in a field built on careful, incremental claims, close to an admission that the rulebook itself may be incomplete. The instrument responsible for catching this deserves its own moment of attention, because Webb was never meant to be a Pluto telescope. It was designed, first and foremost, to look backward in time, to catch the faint infrared glow of galaxies formed in the earliest chapters of the universe more than 13 billion years ago. Turning that same extraordinary sensitivity toward a small, cold world sitting practically in our own cosmic backyard was almost an afterthought when the mission was first conceived. And yet, it is precisely that oversized sensitivity, built for peering across the observable universe, that made this discovery possible at all. No previous instrument, not Hubble, not Spitzer, not even New Horizons flying directly past Pluto in 2015, had the spectral resolution in this particular range to catch a signal this faint and this specific. It took a telescope built to study the birth of galaxies to notice that our own solar system still had something left to hide. And this is where a person watching from home has to sit with an uncomfortable thought. We are not talking about a blurry anomaly in old data that better equipment might explain away. We are talking about the most advanced infrared observatory ever constructed, pointed directly and deliberately at Pluto, using instruments engineered specifically to catch signals like this, and it is still coming back with a result nobody predicted and nobody can yet name. The tool, built to answer our questions about the solar system, has instead handed us a new one. To understand why this rattled the people running the analysis, you need to understand what Pluto was supposed to be. When it was reclassified as a dwarf planet in 2006, the underlying assumption was almost dismissive. Too small, too cold, too far from the sun to sustain any kind of dynamic activity. A frozen leftover. A ball of ice drifting silently at the edge of the solar system. Geologically dead, chemically simple, essentially finished evolving billions of years ago. New Horizons already cracked that assumption open in 2015, revealing mountain ranges, a possible subsurface ocean, evidence of relatively recent geological activity on a supposedly dead world. Webb's new findings do not just support that revision, they deepen it into something closer to unease. Because if Pluto's surface is generating or hosting a chemical compound, unlike anything cataloged in a solar system full of well-studied ice and rock, then something is actively happening there. Some process, chemical or physical or both, is producing a signature this specific, this consistent, and this alien to laboratory science. Dead worlds do not manufacture new chemistry. Only active ones do. And Pluto, by every measure available before 2015, had no business being active at all. It receives less than 1,000th of the sunlight Earth does. Its interior, by the standard models of planetary formation, should have gone cold and rigid within a few 100 million years of forming, leaving nothing but a static ball of ice with no internal heat source left to drive geology, atmosphere, or chemistry of any complexity. New Horizons already found cracks in that model. Nitrogen glaciers appeared to be flowing. Mountains showed signs of being geologically young rather than billions of years old. A possible liquid ocean seemed to be sloshing beneath the icy crust, kept from freezing solid by heat nobody could fully account for. Webb's new findings are not an isolated surprise, sitting on top of an otherwise settled picture. They are the next entry in a growing list of reasons to suspect that the dead world label slapped onto Pluto decades ago was wrong from the start. The mystery does not end at the surface. Just months before this spectral anomaly surfaced, a separate Webb study revealed something almost as strange about Pluto's atmosphere. For years, planetary scientists led by researchers like Xizhang had theorized that a thin haze high above Pluto's surface was responsible for making the dwarf planet colder than models predicted it should be. A haze thin enough that older instruments simply could not detect its glow, buried as it was beneath the much stronger thermal signal bleeding over from Pluto's massive companion moon, Charon. Separating the two signals required exactly the kind of precision only Webb's mid-infrared instrument could deliver. When the data finally came back in 2025, the prediction held. The haze was there, glowing faintly exactly where the models said it should, cooling Pluto's atmosphere in a way that happens nowhere else in the solar system that we know of. Confirmation should have felt like closure. Instead, it opened a door to an even bigger question. Because a haze that behaves like this, one that regulates temperature, drives seasonal cycles of ice redistribution across the surface, and appears to be actively transferring material from Pluto's atmosphere onto Charon itself, is not the behavior of a dead world quietly existing at the solar system's edge. It is the behavior of a system with weather, with cycles, with a climate engine running on almost no sunlight at all, doing something that, by every model built before Webb, should not generate enough energy to sustain it. And then there's Charon, Pluto's largest moon, nearly half its size, close enough that the two worlds technically orbit a shared point of gravity between them rather than one circling the other, like a binary planet instead of a planet and its satellite. In 2024, Webb turned its instruments on Charon specifically and found carbon dioxide and hydrogen peroxide embedded in its icy surface, chemical signatures that help explain how this strange moon originally formed, but which also raise their own uncomfortable follow-up questions about energetic processes happening on a body that, again, was supposed to be inert. Hydrogen peroxide, in particular, does not simply appear on its own. It typically forms when radiation breaks apart water ice and the fragments recombine into something more reactive, a sign of ongoing bombardment from cosmic rays and solar particles reshaping Charon's surface chemistry over long stretches of time. Researchers studying the data noted that future observations targeting the remaining spectral gaps could reveal even more of Charon's chemical inventory, additional mechanisms nobody has identified yet, hiding in wavelengths not yet fully explored. What is striking is how none of these three findings were part of the same investigation. Different teams, different instrument configurations, different years, different questions being asked of the data. Nobody set out looking for a unified pattern connecting an unidentified surface compound, an active haze-driven climate, and an irradiated moon with a growing chemical inventory. The pattern only becomes visible when you step back and look at everything Webb has returned from this one small corner of the solar system in the span of a couple of years. That is often how the biggest shifts in planetary science happen, not through a single headline discovery, but through a quiet accumulation of anomalies that individually look explainable and collectively look like something being missed. It is worth remembering how recently our entire understanding of Pluto was built almost entirely on guesswork. For the better part of a century after its discovery, Pluto was a single point of light, a dot too small and too distant for even the best ground-based telescopes to resolve into anything more than a smear. Entire textbooks were written describing a small, static, frozen world based on almost no direct observational evidence at all. New Horizons shattered that in a single flyby, and now Webb, sitting 1,000,000 miles from Earth at a gravitationally stable point in space, is quietly doing something New Horizons never could. It is watching Pluto, not for a few hours, but repeatedly, over months and years, catching the slow seasonal changes, the shifting haze, the chemistry evolving in real time, rather than frozen in a single snapshot. Each new observation window is another chance for the picture to shift again. That is precisely why the scientific community's caution here matters more than any dramatic headline. A single anomalous spectral line, however strange, is not proof of anything beyond itself. Instruments drift. Calibration can introduce artifacts, overlapping thermal signals from Charon, from background sources, from imperfect atmospheric models, can occasionally produce features that look meaningful and later turn out to be artifacts of the measurement process, rather than the object being measured. The Bézard team's own caution, publishing through a preprint rather than rushing to declare a definitive new discovery, is exactly how careful science is supposed to work. It is also exactly why the not yet explained nature of this signal is more compelling than a premature answer would be. An unclaimed mystery, sitting in a verified data from the most capable telescope ever built, carries more weight than a rushed and possibly wrong explanation ever could. Layer these findings on top of each other, and a pattern starts to take shape, one that no single discovery reveals on its own. An unidentified molecule on Pluto's surface, present in greater abundance than anywhere else observed. An atmospheric haze behaving like an active climate system rather than a frozen relic. A companion moon showing chemical signatures tied to energetic formation processes still not fully mapped. Individually, each of these is a fascinating scientific result, the kind of incremental discovery that fills academic journals every year. Together, they sketch a picture of a world at the edge of the solar system that is far more chemically and physically active than anyone expected a small, sunlight-starved dwarf planet could ever be. Scientists are, of course, cautious about where this leads, and that caution matters. The unidentified 5, 11-micrometer signal has not yet been confirmed in a peer-reviewed journal. The current findings are documented in a preprint, meaning the wider scientific community has not yet had the chance to independently verify or challenge the result, a necessary and normal part of how real discoveries get tested before they're accepted. Some researchers may eventually trace the compound back to an obscure but ultimately mundane organic residue, a more exotic cousin of the tholins already known to exist across the outer solar system. That would still be a genuine discovery, just a less dramatic one than the mystery currently sitting unexplained in the data. But it is also entirely possible that what Webb has caught a glimpse of is something with no precedent at all, a chemical process unique to conditions that simply do not exist anywhere closer to the Sun, conditions our laboratories on Earth have never been able to replicate. What makes this moment different from decades of prior Pluto speculation is the instrument doing the looking. Webb was not built to guess. It was built to measure light with a precision no observatory before it could match, engineered specifically to catch faint signals from the coldest, darkest corners of the solar system and beyond. When an instrument built for that level of precision returns a result nobody can immediately explain, the honest response is not to panic, and it is not to shrug. It is to keep watching, which is exactly what the Bezoar team and others building on their work intend to do, aiming Webb back at Pluto and Titan in future observation windows, hunting for more data points that might finally pin down what this compound actually is. There is something almost poetic about the timing of all this. Pluto was discovered in 1930 by a young amateur astronomer working from a mathematical hunch, then spent nearly a century as the misunderstood edge of the map, first celebrated as the ninth planet, then demoted to something smaller, something lesser in the public imagination, a decision still debated by scientists and the public alike 2 decades later. New Horizons gave it back its dignity in 2015, revealing a world of mountains and ice and startling complexity that no telescope on Earth could have shown us. And now, a decade later, the most powerful telescope ever built is looking at that same small world and finding a chemical signature that does not exist in any human catalog. Pluto, it turns out, was never finished revealing itself. It was simply waiting for an instrument sensitive enough to hear what it had been saying all along. None of this means anything sinister is happening at the edge of the solar system. There is no evidence here of anything beyond natural chemistry and physics behaving in ways our models did not anticipate, which is, in its own right, one of the most exciting positions science can find itself in. Every unexplained signal is either a mistake waiting to be caught or a discovery waiting to be understood, and right now, this one is still an open question. The compound on Pluto's surface does not yet have a name. The processes generating Pluto's unexpected climate behavior are not yet fully modeled. The full chemical inventory hiding in Charon's ice is not yet complete. Webb will keep watching, the data will keep accumulating, and somewhere in a research lab, a spectrum that currently matches nothing will eventually either be matched to something known or confirmed as something genuinely new to science. What happens next depends entirely on observation time nobody can guarantee. Webb's schedule is oversubscribed years in advance, competing proposals from thousands of researchers across every field of astronomy, all fighting for a limited number of hours pointed at a limited number of targets. Getting the telescope turned back toward Pluto for a longer, more detailed follow-up is not automatic. It requires a case compelling enough to win out over the search for the earliest galaxies, over exoplanet atmospheres, over supernovae and black holes, and everything else competing for the same instrument. An unidentified molecule sitting quietly in a small, cold, unglamorous corner of our own solar system has to earn its place in that queue, the same way it earned its place in this story, by being strange enough that nobody can afford to look away. And that, in the end, is what makes this moment different from a century of prior Pluto speculation. Not that we have finally found an answer, but that, for the first time, we have an instrument capable of asking the right question and returning a result too specific, too consistent, and too strange to simply dismiss. Somewhere in that data is a chemical process the outer solar system has apparently been running for billions of years without a single observer noticing, until now. Until then, 3 billion miles away, a small frozen world once dismissed as a dead relic continues doing something nobody predicted. Glowing faintly in wavelengths of light we only recently learned how to read, holding onto a secret that even our most advanced telescope has not yet learned how to translate.